a gas law using STP conditions. So I'm going to start off with looking at my gas laws a little bit differently than we had in the previous example. Boyle's law can be written as PV equals a constant. Charles' law, V over T equals a constant. Avogadro's law, V over N equals a constant. Now if we combine them all together, we get PV over NT equals a constant. And rearranging this a little bit, we can get PV equals N times the constant times T. Now instead of writing the word constant all the time, we can replace that with a letter. And I'm going to pick the letter R. So I get then PV equals nRT. And this is known as the ideal gas law. So we're going to use this gas law anytime we have just one set of conditions. There is no ones or twos here, just one set of conditions, and it really combines everything that we need. Now one thing about ideal, what do they mean by that? Well, some gases are what we call ideal gases, and then other gases are more like real gases. So let's take a look at the difference between the two. Real gases have a mass. An ideal gas has no mass. Real gases have attractions for each other, so they'll pull at each other and probably not occupy the volume you might think, whereas ideal gases have no attractions, so they always occupy the volume that the gas laws would predict. A real gas could condense to a liquid if you cooled it enough or pressurized it enough, whereas an ideal gas would never change to a liquid, no matter how much you pressurized it or cooled it. Real gases obey the gas laws sometimes, just like you obey laws sometimes, but the ideal gases would always obey the gas laws under all conditions. So under what conditions would real gases not obey the gas laws? Well, anything that puts the particles close enough together would cause them to not obey the gas laws. That means high pressure or low temperature. Now for ideal gases, the noble gases are closest to ideal. Probably helium is the most ideal of all of them. And so here are a couple of examples of real gases, CO2 and ammonia, and here we have a couple of noble gases, neon and helium. Alright, so let's take a look at the formula now. PV equals nRT. I'm going to show you how we can derive the value of R. And once I show you that, we're going to use the same value all the time. So you'll never be asked to derive it again. Just want you to watch this. So all I have to do to figure out what the value of R is to have known conditions of pressure, volume, moles, and temperature. And I do. I know that 1 atmosphere of pressure at 273 Kelvin, which is STP conditions, will occupy 22.4 liters if I have 1 mole of a gas. So I'm going to plug all that data in and solve it for R. And I get this very, very small number, 0.0821. And notice all 4 of the units stay. It's liters times atmospheres over moles times Kelvin. Now that means that if you want to use this gas law, you have to have the volume in liters. So you might have to convert that. You have to have the pressure in atmospheres. You have to have moles, not grams. And then you have to have Kelvin. And if you don't have these units, you're not going to be able to solve the problem. Now here's an example. You can see an aerosol can here. We want to know what is the pressure in millimeters of mercury in a 750 ml spray can that contains 2.20 grams of CO2 propellant at 25 degrees centigrade. So all of these aerosol cans have a propellant in them, some gas that will carry out your liquid. The reason you shake up that container is because the liquid always settles to the bottom, and you want to try to get that liquid to come out as a nice spray. So an aerosol actually means a mixture where you have a liquid spread throughout a gas. So let's do some calculating. First thing we want to do is write down our gas law. And we want to solve it for our unknown, which is going to be pressure. So pressure, we'll go back on this, pressure equals nRT over V. And then we want to have all of our factors. Now we need nRT and V. Now N is moles, so I'm going to have to convert my 2.20 grams of CO2 to moles. So moles would be grams divided by the molar mass. Molar mass of CO2 is 44, and that gives me 0.0500 moles. So I'm giving you three significant figures. Now R is the gas constant, so I already know that. Here it is here. Now temperature, I need 25 centigrade converted to Kelvin, so I just add 273 to that. And I need the volume in liters. I'm going to have to convert 750 milliliters to liters. And then I plug it into my formula, and you can see that everything will cancel. Moles will cancel, liters will cancel, Kelvin will cancel, and I get an answer in atmospheres. And because my question really asks for the pressure in millimeters of mercury, I have to convert my 1.63 atmospheres to millimeters, and so I'm going to use my conversion factor, 760 millimeters to an atmosphere, and then I get a final answer of 1240 millimeters of mercury.